Okay, well, I realized I forgot to do the intermediate value theorem, and I also wanted to do one more example of sketching a polynomial at this point. Okay, so the intermediate value theorem. If you take calculus, you'll see this again. So what I'm going to do, instead of writing it out in words, you can read about it in words in the book. I'm going to describe what the intermediate value theorem says. What it's trying to tell us. So it says you have some function. We'll call this f of x. And there are two values of x equals a and x equals b. And if you go up to the function and then read off to the left, you get the values of the function. So at x equals a, the value of the function is this value. You read that off the y-axis. Same thing here. This is f of b. So f of a is not equal to f of b. Obviously, x equals a is not equal to x equals b because they're different points on the graph. But f of a is not equal to f of b. So what you have is you can pick any value between f of a and f of b. We'll call that k. And it's saying that there's a value of c between a and b. So along this axis, you can pick some value of c where f of c is equal to k. Okay, so what we're saying is you can come along here and you can kind of eyeball it. There's some intermediate value c such that f of c is equal to this value k. Now we don't know exactly what that is. We'd have to solve the equation for it. In calculus, they give this example of you've got a skydiver and he falls through 10,000 feet and he used 5,000 feet. And all we know is that, we know at some time, earlier time, that he's at 10,000 feet. Some later times at 5,000 feet. Well, we know that between those two times, he has to fall through every intermediate value between 10,000 to 500. He doesn't just jump magically. He doesn't disappear and reappear somewhere else. So that's why it's called the intermediate value theorem. He's going to take on every value. In this case, the y value would be his elevation. The x value would be the time. X sub a would be the time that he falls through 10,000 feet. And x sub b would be the time that he falls through 5,000 feet. And then you could pick 7,000 feet, and there's some time between the beginning and the end where he falls through that height. Okay, so what does that have to do with this particular chapter? Well, what it's saying there is that if you had some, let's say, x equals 1, where the value of the function is down here, let's say it's negative 4, and then you have some other later value, x equals 4, where we know that the y value is, say, positive 4. Well, what we can do is we know that somewhere this function crosses the x-axis because the y value is negative at this point, and we know the y value is positive at that point between 1 and 4. What the intermediate value theorem says is there is a 0 somewhere between x equals 1 and x equals 4. We don't know where exactly it is, but we know it's there. So you could do some guessing, and the closer you guess, the closer the value, the y value is going to be to 0. When you get the exact guess, then you get a y value of 0. So it's kind of it would be more of an iterative process. You'd guess an x value. You'd see what the y value is. In calculus, we actually use calculus to come to the answer much more quickly than we could here. So that's the intermediate value theorem. So I'm just trying to think if I give you an example of something like that. Well, let's make up a problem where we know where the 0 is by making it in factored form. Okay. So you can see I've got zeros. I've got a 0 at x equals -1, 0 at x equals -2, 0 at x equals 3. Now, if I multiplied this thing out so that it was in its non-factored form, then I wouldn't know this. You have to have these you'd have to have these things factored to know this. So I'm just trying to decide whether to go ahead and multiply this thing out. Yeah, let's do that. So I'm going to make this multiplied out. So if we multiply the first two terms together, we'll get x squared plus, so use FOIL, you get x squared plus 3x plus 2. And then we multiply by the third term. Now it doesn't matter which order you do these in. I just chose the first two. So you get x squared plus 1x plus 2x, which is 3x plus 2. Now you can multiply these together, and what you would get is if you multiply x times each one of these, you'll get x cubed plus 3x squared plus 2x. And then we have -3 times all those two terms. And I'm going to put them just below so I can add them kind of like we do normal adding. So you're going to have -3x squared, -9x minus 6. So we add those two things together, we'll get x cubed. These cancel out, minus 7x minus 6. So that's the equivalent expression. F of x is also just x cubed minus 7x minus 6. Let's just prove that's true. So I'm going to open up my graphing program here. And I'm going to write out both equations, and they should be right on top of each other. So you've got x plus 1, x plus 2, and x minus 3. So this is the factored version. X plus 1, x plus 2, x minus 3. Okay, so here it is. Graph. Okay, I can zoom out in the y direction. So we got intercepts at -2, -3, +3. Okay. Did I do that right? -2, -1, +3. Okay. Now if I plot this, x cubed minus 7x minus 6, I should get the same graph. So they should just lay on top of each other. So we've got put a semicolon x cubed. I forgot what it was, plus or minus. Let's try. I'll move it out of the way in a second. Minus 7x minus 6. Okay, graph it. Okay, that apparently was right. So you can see the red and blue curve are the same curve. So I did that right. Okay, now let me just minimize that thing. Now, so let's say I was given this equation and I didn't know it was factored. So if I did, let's do f of +2 and f of +5. So we're going to evaluate the functions at those two x values. So what you'd get is you get 2 cubed minus 7 times 2 minus 6. And here you would get 5 cubed minus 7 times 5 minus 6. So let's plug those in my calculator. So you get 7 cubed minus 7 times 2, which is 14, minus 6. So that's negative 12. And then you've got 5 cubed minus 35 minus 6, and you get 84. So what we can say is that since the y value goes from negative to positive, there must be a 0 between x equals 2 and x equals 5. That's the intermediate value theorem. Now you'd expect, because this one is more positive than this one is negative, you might think, oh, it's probably closer to 2 than it is to 5, because this has more chance to become positive. So you might pick 3. So you'd say, okay, how about 3? How about 3? Because you probably pick integers to start with. So then you say, okay, let me try that. F of 3. So you do 3 cubed minus 7 times 3 minus 6. So 3 cubed minus 7 times 3 minus 6. Did I do something wrong? Yeah, I did. 3 cubed minus 7 times 3 minus 6. I'll get it right one of these days. Minus. I get 0, okay. Now in this case I just got lucky. But, you know, I'm assuming that I don't know any of this. I just used this to come up with a problem to show you. So that's the intermediate value term. And, you know, if I picked 3 and 3 gave me a number which was close to 0 but wasn't exactly 0, then I may be able to make a better guess. In this case, I just got lucky in it because I picked an integer. If it was a non-integer, I'd still pick an integer. And then after I get close enough with an integer, I'd try to then pick some non-integers, some decimals. Okay, so that's the intermediate value there. Let's do one more of these problems where you sketch. So again, in this section, we're giving you problems that you should be able to factor reasonably easy, because we haven't learned how to figure out the zeros of third-order polynomials yet. Okay, so it's a third-order polynomial. And you can see if I look for a common factor to factor out of all of these, I have got 3x, because I can divide 15 by 3, I can divide 18 by 3. They all have x in them. So if I factor out a 3x, I'll get x squared minus 5x plus 6. And now, luckily, I can just observe the last polynomial and factor that as well. So that's x minus 2 and x minus 3. And you can see that works. Okay, so what can I say? First thing is the end behavior. Well, because that's a positive 3, the coefficient in front of the x cubed term, that means that the end behavior looks like this. It's an odd function, so it's going to start one direction, go the other. It's positive, so it's going to start here at negative infinity in the y direction, and it's going to come up. We're going to do some things in the middle here, and then at the other end it'll go up to that. If this was negative 3 or negative 3, then it would go this way, the other way. If it was an even highest order term, then we would either have them both going up or both going down. So that's just kind of, we'll come back to that, but that's what you mean by end behavior. The second thing is to find the zeros. Well, that's easy because I've already had it factored now. So I have 3 zeros, one being x equals 0, The other one being x equals 2, because if I make x equal 2 here, this will go to 0, and x equals 3. So these are the zeros. The x-intercepts are going to be the points 0, 0, 2, 0, 3, 0. And then finally, we're going to pick some other points. So what we did previously is we broke this up into 3 intervals, from negative infinity to the most negative number, which is 0, then to the next most positive number, which is 2. These are all along the x-axis. Then from that number 2 to the next 0, or the next x-intercept, and then from that to positive infinity. So this is all real numbers except 0, 2, and 3. And then you pick numbers inside those intervals. And what I'm doing is I'm picking them just outside of the intervals, because if you pick too far out, if you picked, say, negative 20, you'd have a really big number, and that would not be good. So now we have to evaluate this original function, and not well, you could do it in the factored form, but it's probably best you just use this one. So let's write that out. So we have 3x cubed minus 15x squared plus 18x. I think that was the function. Yep. So we just plug that into our calculator. So 3 times negative 1 cubed minus 15 times negative 1 squared plus 18 times negative 1. So the value of this function here is negative 36. If I plug in positive 1, I'll get 6. If I plug in 2.5, I get negative 1.875. And if I plug in 4, I'll get 24. Okay, hope I got that right. Well, let's plot this graph just to, or did we already? No, we didn't do this one. Okay, I'm just going to plot this thing just to make sure I haven't made a mistake. 3 times x cubed minus 15 times x squared plus 18 times x. Plot that thing. So here it is. So 0, 2, and 3. F of negative 1 is negative 36. So I got to zoom out a little bit here. So that looks about right. Negative. Okay. F of 1 is around 6. That's good. F of 2.5 is around negative 1.8. Yep. And F of 4 is around 25. Okay, so those all make sense. So now what I would do is I would plot this thing. So let me get a piece of graph paper. And once we learn how to get zeros a little more accurately, or from equations that are not as easily factored, we're going to get a lot of practice at doing this. So now what I'm going to do is I have to pick my scale, which I'm going to go from -10 to +10 on the x-axis, but I'm going to adjust the scale in the y direction, and I have to go up to 30, down to -36. So I'm going to put marks every 2 and make them 10. So you'll have 10, that's 10, not 50, 20, 30, 40, and then down the other side here. -10, -20, -30, -40. Okay, so let's plot what we have. We've got the x-intercepts, which are 0, 2, and 3. And then we have these extra points. So -1, -36, that's about right there, because there's 30, 40, 35. Okay, then 1, 6, which puts you about there, because there's 10. 2.5, -2, basically. So that goes right there. And 4, 24. 1, 2, 3, 4, 10, 20, 24. So now we have all these points, and then we just sketch the graph. So we come through this point. The end behavior says that we came from -infinity. We go up here. Oh, I forgot the y-intercept. Let's go back and do that. So the y-intercept, we take the unfactored version. Actually, the y-intercept is 0, because you can see if I stick x equals 0 in here, I'll get 0. So the y-intercept is going to be 0, 0, which is also x-intercept. Okay, back to here, back to drawing it. So we come up here, there's our y-intercept and x-intercept. Then we come up here through this point, back down through the x-axis, down through that point that we just calculated, and back up through this point. So how many points did we have? 1, 2, 3, 4, 5, 6, 7. 7 points. Okay, so that is how they work. This is a third order polynomial, has 3 real zeros, and by factoring the initial expression, by taking out a common factor out of all 3, we were able to reduce it down to a second order polynomial, which we could factor. So that gives us the 3 zeros. Plugging x equals 0 in here gave us the y-intercept. The end behavior says it started down here. So it comes from this direction, which is pretty obvious once you put these points in. And the end behavior on this side goes up this way. And then we picked 4 other points that were not too far from the zeros, because if you go too far from the zeros, you're going to be way off scale. And it's going to be hard to plot the stuff.